Okay, somebody has said something. Okay, good afternoon. Thank you, Tanmay. Tanay, sorry. So this is our second problem, which again says obtain the state table, state diagram, and state equation for the circuit shown below. So now, can somebody tell me what is the difference between the previous one and this one? What's the difference? So here, what we are going to do is we will be using a JK. What you can see is a JK flip flop and not D and T. So you need to be slightly careful when you look at JK, D and T. Now, if you just recall that the D flip flop excitation table Qn and Qn plus 1, 0, 0, 0, 1, 1, 0, 1, 0, 1. So this is 1 and this is also 1. So here the excitation table of the D flip flop was 0, 1, 0, 1. So that is why we could write D is equal to Qn plus 1. But for JK, it is going to be 0, 1, XX and XX 0, 1. About 1, 2. So that is something that we have to keep in mind when we are doing the excitation table. We are trying to make the state table using JK flip flop. JK flip flop has got two inputs and D and T has got just one input. So obviously when the number of inputs are less, our trouble is also less because we don't have to think too much about the excitation, about the inputs. However, JK flip flop gives lesser hardware as compared to D and T, but that might not always be true. So in a way, it depends. Just for the record, my screen is visible to you or not?
So visible.
Okay, but I am not able to see it. So let's. Okay. So this is the point that you have to note. Certain things you can straight away see from this thing. If you just backtrack, this point is QB and this point is QA. So as soon as you see the circuit, don't see what it is, just try to observe the connections for some time and you can see here that this QA goes to the next flip flop. Let's call this as flip flop 1 and let's call this as flip flop 2. So this is my input X. So let's track it from here. So here you will get X bar. If you backtrack this input, this is nothing but QB. So here you will get X bar and QB. So we can simply say J1 is equal to QB and K1 is going to be equal to, this is a AND gate, so dot X bar dot K. So this is as far as the first flip-flop is concerned. If you look at the second flip-flop, the J is coming from here. So this is how the J is. If you track this thing, you should be able to see this. So J2, as you can see, J2 is X bar and K2 is going to be, you can see again here, this is nothing but the same signal. X is coming over here, so that is going to be X dot QA, X dot QA. So you can again say J2 is X bar and J2 is going to be X dot QA. So these are our findings. Now why have we done this? Why have we done this? Because we want to you know write the state table, and state table is in terms of the outputs and the next state outputs. So that is why we are slightly interested in this thing. So I will just note this properly. Okay. So these are the two findings from this particular subject. Obviously, you should also see the Z, because output is very important. So you can again backtrack and look at this point. This is QA bar, and if you look at this point, it is nothing but QB. So obviously Z would be equal to QA bar. This is which gate? It's a XOR gate. This is QA bar XOR QB. QA bar XOR QB. So that gives me my third equation. And you should also see that the clock goes simultaneously to both the flip-flops, and that is why this circuit is basically a synchronous circuit. Now, my question to you all, whether the given circuit is a Moore circuit or a Mealy circuit, post your answers in the chat box. Whether the given circuit is a Moore circuit or a Mealy circuit. Yes, can somebody unmute and answer this question? Okay, I can see some answers coming. Let me just have a look. Okay. So many of you have said more circuit. Okay, but Hemant and Darshan have said Mealy. Uh, Darshan, can you unmute and tell us why?
Yes, sir.
Darshan, why do you feel it is a Mealy circuit? Why do you feel that it is a Mealy circuit?
सर कारण लास्ट टाइम कसं मी तुम्हाला विचारत त्यावरून इनपुट एफएक्टची आउटपुट सर
No, you are not audible. Can you speak a bit clearly or loudly? Hemant, can you answer the question? Why do you feel it's a Mealy circuit? Hemant, I think both are having network problems. Except these two, others all have given the right answer. Now, the reason for that is very simple. All you need to do is look at Z. You should look at Z. What will you look at? Z. Now, Z is a function of only QA and QB, only the present states. It is not a function of Z does not have X in it. Does not have X. Can you see X in the function of Z? No. So that is why it's a Moore circuit. If there would have been some one more line like this from X inside this, then we would have said that it's a Mealy circuit, but no such thing is present. So that is why this circuit is called as a Moore circuit, not a Mealy circuit. Okay, just rub it off. It's not required. Hemant and Darshan, have you understood this point?
Yes, sir. Yes, sir.
So let's go ahead with the state table.
Sir, I have doubt in K2, sir. I didn't understood how we calculated K2.
K2. Okay. So, okay. I got why you didn't understand because it is wrong. So, this K2, this is a XOR gate, right? So, this will be
Yes, sir.
XOR. Is this Tanishq?
Yes, sir.
Yeah. So, you should say that it is wrong. Why did you say you did not understand?
Sir, no, I thought some De Morgan law might have used.
No. So, everybody, thank you, Tanishq. Everybody just make that correction. J2, K2 is X XOR QA. Simply because here we are having a XOR gate and here you are having a QA and here you are having a X. So that will XOR the thing and that will come at the input. Good. Okay, so please note J1 and K1, J2 and K2 along with Z. Now let's go to the state table. Now state table here is also something similar like before. Instead of just D flip flop, now we have J and K instead of that. So that is fine. But the real skill here is to actually find out what is the value of QA plus and QB plus. So first, I would like you all to start copying this table. You can see that JA and KA. So I am not using the notations uh, J1, K1. I am using the notations JA and KA, and here JB and KB. So that is why here, that is because I am using here QA and QB. So Conventionally, in all the books, they use uh, KA and KB and JA and JB. So anyway, these are my two outputs. So I will just write JA, JB and KB. You can see JA is equal to QB, KA is equal to X bar. That bar comes very small somehow, and JB is also X bar, and KB is QAX, and other things there, as you can see. Now, I'm just dividing this table into some parts so that our understanding becomes a slightly clear. So you can see this part is all present state outputs. Now present state outputs are actually QA and QB only. They are QA and QB only. But just a minute. They are QA and QB only. But you can see that maybe we may require QA bar and QB bar somewhere later, while when we calculate JAK, JBKB, or even Z. So in this case, you can see the Z. Z does not have QA, it has got QA bar. That is why whenever I write QA, I also calculate QA bar, and whenever I write QB, I also calculate QB bar. And this is logical also because QA and QB are the outputs of the flip-flop, and flip-flop anyways has got two outputs, that is the output and the complement of it. So we can always write QA and QA bar, that is absolutely not a problem. So you can see the next is input, that is X. So X also can take two values, X and X bar. So here you can see KA depends on X bar, JB depends on X bar. So we require not X, we require X bar also. So actually we were writing just QA, QB and X. Actually we can write just QA, QB and X. But somewhere here the input of the flip-flops might have terms which are complementary. So that is why we are calculating this upfront. Now comes the actual inputs of the flip-flop. So how do we write these inputs? By looking at the circuit. So how do you fill this table of J, K, JB, KB, and by observing given circuit. By observing given circuit. So you observe something and then you write it. Okay. Now comes the next challenging part. Now I want to answer from you. How will I write QA plus and QB plus? How will I write QA plus and QB plus? There are two ways of doing it. I want an answer from you. Just recall when it was a D flip-flop, QA plus was equal to DA and QB plus is equal to DB. Now I want the answer from you stating how I have written QA plus and QB plus. Yes, anybody can unmute and answer. So the question is open for discussion. Yes, who wants to answer this question? So again, I'll repeat the question. In the problem number 1, we had just DA and DB instead of JAKA and JBKB. And from the excitation table of D flip-flop, we saw that QA plus is equal to DA. QB plus was equal to DB. So with that same analogy, can you write QA plus and QB plus? That is the first question. Is it possible or not? And my second question is, if not, then what is the alternative approach?
Sir, here it is not possible.
Uh, Not possible is not an answer. Anything is possible. Think how I have written. Anyways, I'll give you the answer, but still. Okay. My first hint is, look at the state equations. Look at the state equations for the JK flip-flop. So state equations are also called as your transition equations or excitation equations. So I want you to look at the equations of the JK flip-flop. So you can see QA is JA, or QA plus will be JAQ A bar plus KA bar QB, something like that. So that is going to be the case. So the transition equations will be like this. I'm just writing it down. QA will be J Q bar plus K bar Q, something of this sort. Or I will say Q plus. Q plus is going to be in this way. That is, the next state output will depend on the present state inputs and the present state outputs. That's what it is. But now if you look at this equation is really very clumsy, because there are three inputs, J, K and Q, and we may have to add more columns to find out J Q bar, K bar Q, and then OR it, and do this thing twice for QB as well. So what I thought, let us devise a shortcut for looking at this thing. Now just recall from our previous discussions. I'm just writing it down here. So this is Qn, this is Qn plus, and here we have Jk. So if you look at this, this is 0, 0, 1, 1, so 0, 1, 0, 1, and Jk would be 0, 1, xx, and this would be xx, 1, 0. Okay, whatever it is, doesn't matter. Now, you should also note that Jk are my present inputs and Q is my present output, and I want to now write Q plus. So I'm just drawing these columns for your. So I go to the basic definition of the JK flip-flop. So here we have 0, 0, 0, 0, 1, 1, 1, 1, and K can take values of 0, 0, 1, 1, 0, 0, 1, and 1. Now, for any values of J and K, there can be two possible outputs. So that can be either 0 or 1. This can either be 0 or 1. This can be 0 or 1. Or this can also be 0 or 1. That is quite possible. Now, the basic definition of JK flip-flop tells me that when I give J and K as 0, 0, the output should be no change. When I give 0 1, it should be set. When I give 1 0, it should be set. And when I give 1 1, it should toggle. It should toggle. That means if it is 1, it should become 0. If it is 0, it should become 1. Toggle. So now if you apply this logic on this, it is very easy. No change means what? Whatever I have written in the present state, the same thing will come here. Reset means what? Everything will become 0. So whatever is state, the next state is going to be 0. Set means what? Whatever is the previous state, the next state is going to be 1. And toggle means what? If the previous state is 0, this will become 1, and if this is 1, this will become 0. So now we will use this basic definition of the JK flip-flop to determine the next state of the JK flip-flop. And that is exactly what I am going to do in this case. So you can see that when I am calculating QA plus, when I am calculating QA plus, I shall be looking at QA, I shall be looking at JA, and I shall be looking at KA. So naturally, you can relate it to this. If this is QA plus, then I should look at QA, JA, and KA. If I want to calculate QA, I should look at QA plus. I should look at QA, JA, and KA. So are you all able to identify these three? QA, JA, and KA. Now the same logic I would apply in this context. So you should see here, this JA and KA is 0 0 in the first case. So this condition 0 0 means no change. Then next case JA and KA is 0 0, again no change. 1 1 means toggle, 1 0 means set, 0 0 means again no change, 0 0 here, again no change, 1 1 toggle, and 1 0 is again set. So we are looking only at JAKA and deciding what the output should be. But we already have a present state output, that is QA. So now when JA is 0 and KA is 0, that is the first case, what are we expecting? No change in the output. We are expecting no change in the output. So if it is QA, if QA is 0, no change means QA plus should also be 0. If you look at the second condition, here JAKA is again 0 and 0. So NC, that is going to be no change. No change in what? Present state output. What is the present state output? 0. And since I give J and K as 0 0, there is going to be no change. So I'll get here 0. Now the next one is the third row. If you see 1 1, JA and K is 1 1, that is toggle. So toggle means if previously it is 0, it should go to the next state should be 1. It should toggle. It should toggle. Then after that, if you see 1 0, this is going to be set. Set means what? The output should be 1. No change, again 0 0. So if it is 1, again no change here, it will remain 1. Again next JK is 0 0, that is no change. So the present state output is 1. So again no change means it will remain as 1. 1 1 means toggle. if it is 1 here, it should become 0. So you can see this toggle condition, that is, it is going to toggle. And then again 1 0 means set. Irrespective of what QA is, 1 or 0, the output will become 1. So that is why I have written here 1. So you can see that in these two places, if you observe QA plus, where I have put a box, those are my toggle conditions. And for toggle, you need to see what is the previous state output, that is our present state output, that is 0. If it is 0, it should go to 1. That is toggle and go to 1. And if the present state output is 1, it should toggle and go to 0. On a similar basis, now you should solve, you should see QB. So for QB plus, if you want to calculate QB plus, you need to have JB, you need to have KB, and you need to have QB. This is the way you can calculate QB plus. So come on, see whether you are getting the same thing or not. So in the first case, 1 0 means we have set, 0 1 is going to be reset. Then 1 0 is again going to be set, 0 1 is going to be reset, 1 1 is toggle. Then we have here 0 0 is no change, 1 1 is again toggle, and 0 will be no change. So I can just identify the toggle conditions. You can see here 1 0, and if you observe here QB, that is 0 1. So if it is 0, it will toggle and go to 1. If it is 1, it will toggle and go to 0. So this is the way you have to do it for JK flip-flop. That is why I took this example so that you can solve it. Yes. Any doubts in this? Ask. You may have one doubt, that is how do we write JA and QB? So we wrote JA is equal to QB. So whatever is in QB, we wrote it in JA. Then we wrote KA as X bar QB. So we saw X bar and QB, took a AND logic of that, and we wrote KA. And similarly, JB is X bar, AB is QA XOR X. And Z directly QA bar plus QB. So it's just a OR. Any doubt in this, please ask. Once you are done with this state table, you can say done in the chat box. Karthik, are you there?
Yes, sir, I'm there.
Okay. Once you finish writing, just let me know.
Yes, sir.
So that is why many times we prefer a D flip-flop over JK and T, because we can straight away copy whatever is in DA into QA plus and whatever is in DB into QB plus. But if we use some other flip-flop, then also we can design. It's not that we cannot design, but yes, we have to do some or take some more effort. Yes, if there are questions, please unmute and ask. I am waiting to answer these questions. Get everything clarified properly, because now we are coming at the end of chapter number 4, and that's where the real digital design actually ends. And there are a few theory topics left, which we will just cover in the next 2 weeks, and that will be the end of it. Your IA is on 29th, and syllabus will be based on, department has not yet intimated, but it will be something similar that we used to have before, that is 40% of the syllabus, which is approximately the first 2 chapters. So that should be the syllabus for your IA. And as far as that first 2 chapters are concerned, you have to do a proper reading. The questions would be multiple choice, and the difficulty level would be somewhere between MU and GATE. Excitement table of JK. Prathamesh, Akshay, don't call it excitement table, okay? Call it as excitation table. Okay, excitement table slightly becomes different. You get excited when you get the table. It means that. Akshay, have you understood that? Okay, so I think it's a typo error, but anyway, in the exam, don't write excitement table. The examiners will laugh like anything and then give you a 0. So it is excitation table. So there are so many tables that we have seen. We have seen starting with truth table. Then we have excitation tables of the flip-flop. And then we have state tables. So 3 different types of tables. Okay, so let's go ahead. So this is just for your information. Okay. Now from the state table, you will make a state diagram. From the state table, you will make a state diagram. Come on, make it. From the state table, you will make a state diagram. So before that, you should observe this. This is the compressed version of the state table. That is, if QA, QB is 0, 0, 0, 1, 1, 0, and 1, 1. You should look at what is when x equal to 0 and when x equal to 1. What are the next states? So that's what we have written. So I'll just identify one for you. So you can see here, I'm just rubbing something from this table. Okay. So just look here now.
Hello, sir.
Yes.
सर आउटपुट मध्ये एक्झॉर आहे ना सर तुम्ही फक्त ऑर केलंय
म्हणजे
इट्स क्यूए
Yes,
बार
sir.
तो पूर्ण आउटपुट रॉंग येणार ना
not really, because it is exclusively or, na?
येस सर
Yeah, so exclusively or, so in these two cases we have 0 0. That's it. Okay, so just to reduce our error, what we will do is we will place a, and instead of, just a minute, huh? So what we will do is we will make this on. Okay, decide to change the diagram, so we can continue with the same. Okay, is it okay? Who was this? Darshan, is it okay now?
Yes, sir.
So actually circuit doesn't matter, but the way you are going to calculate the thing matters. And you must observe that Z is just a formality actually. It can be anything. It can be Z can be QA plus dot QB dot QA, some anything. So Z is some output, but it is only used to determine whether it's a Moore or Mealy. Used to just determine whether it is Moore or Mealy. That is the basic thing inside Z. So we can make this as or. So thank you for noting that QA plus is, it is plus QB. That's it. QA bar plus. So since we have done the small change in the output itself, this still stands true. And those who feel that no, I want to go with XOR only, then you should look at these two positions. This is 1 1 and 0 0 should be, so this should be 0 0. That is the change that you should look at. Okay, anyways. Now coming back to the state diagram. So I want you to look at the first two conditions. I want you to look at the first two conditions. So you can see here QA is 0, QB is 0, QA Vishwas, can you hear me? Because I had an interruption in between. Darshan, can you hear me? I had an interruption in between.
Yes, sir.
सर ऍक्च्युली तुम्ही 2 मीटिंग मध्ये आहात म्हणजे दुसऱ्या मीटिंग मध्ये म्यूट वर आहात
That is okay. You are able to listen to me, na?
येस सर
You are able to see me also, na?
हा सर
That's fine. So if QA and QB is 0 0, you can see if X is 0, then the next state is 0 1. And if QA and QB is 0 0, and if X is 1, then the next state is going to be 0 0. So first is 0 1 when X is equal to 0, and the next state is going to be 0, 0 when x is equal to 1. So this is what we saw. If the present state is 0, 0, when x is equal to 0, the next state will be 0, 1, and when x equal to 1, the next state will be 0, 0. And this same thing you can just backtrack for your own sake. So please copy down this particular diagram. Now, why we should write this table is because it is easier to draw a state diagram from this table rather than the previous one. So if somebody says that I will draw state diagram from this table itself, fine, you can go for it, no problem. But there is a possibility that these zeros and ones can confuse you. So it is very much essential to write it very clearly that when x equal to 0, your next state would be 0, 1, and when x equal to 1, your next state would be 0, 0, and the output will be 1. And this is for the present state of 0, 0. So start drawing the state diagram. So how many states can you see? Okay, let me note down. Okay, Aditya Shirsat. Aditya Shirsat, can you unmute? Aditya Shirsat. Vaibhav Shenoy, can you hear me?
सर तुम्ही आता मला हाक मारलात का? मी
No.
डिस्कनेक्ट झालो.
No. Vaibhav Shenoy. Vaibhav Shenon. Okay, Divya Jain. Okay, Parth and Hemant, I got your answers, but I am not actually interested in the answer. It is very clear. I want some people only to answer this question. Okay. So let me just select it. Okay. Anusha Sarla, can you unmute? Anusha Sarla, can you unmute?
Yes, sir.
So my question to you is that how many states can you actually see? I think Anusha is not in proper network. Okay, we'll move to somebody else. Okay, Mitali Bandekar. Mitali Bandekar.
Yes, sir.
Yeah. So now I will ask you some questions and you will give me the answer. The objective of asking this question is I want to know whether you can read the excitation table, the state table or not. Okay. So let's go back and see the. Okay. Now I want you to say that clearly you can see Parth and Hemant, they have answered that we are having 4 states. Do you agree that these are the 4 states?
Yes, sir.
Okay. My next question is, are the outputs corresponding to the states proper, or is there an error in that?
Correspondent.
Sir, they are correct.
They are correct. Okay. Now, everybody should note down these particular questions because I may ask such questions only in the IA. Okay. I will give you a state table and I will ask you whether the state diagram is right or wrong. So you should be able to identify whether there is an error or not. Okay. So it is somewhat that way. Okay. Now, can you tell me, Mitali, you are there, right?
Yes, sir.
What is the next state, or for the present state 1 0, for the present state 1 0, what is the next state when x equal to 1?
Sir, it is 1 0.
It is 1 0. Okay. What is the next state of the present state 1 1 when x is equal to 0?
It is 0 0.
That is right. What is the output of the present state 1 0 when x is equal to 0?
1 1.
Wrong. This is why I am asking you this question. I will again ask the question, Mitali. For the present state of 1 0, when x is equal to 1, what is the output?
It should be 1 0.
Wrong. Again, I am asking you the question. For the present state 1 0, when x is equal to 1, what is the output?
Only 0.
Ah. So, what is the error that you are doing? I was asking you output, but you were looking at the next state. Okay. So this is the place where the students do mistake. Now, if I would have asked you what is the present state output for the present state output 1 0, what is the output when x is equal to 0?
Hello, sir.
For the present state output 1 0, what is the output when x is equal to 0? For x equal to 1, the output was 0.
Yes.
For x equal to 0, what is the output?
0.
Okay. So my next question to you again is, do you really have to see the next state to tell me what the output is?
No, sir.
So why were you getting confused? Now this is true only for a Moore circuit. This thing would be true only for a Moore circuit because we saw that Z is equal to QA bar plus QB. So Z is not a function of X. That is why we can directly write Z on the state. So again, I am just telling you this thing so that you keep that in mind. Okay. Now coming to Mitali, thank you. You can mute your microphone. Next is Sanjana. Sanjana,
Sir?
Sanjana, can you hear me?
Yes, sir, I can hear you.
Okay. Now you have to tell me, if my present state is 0 0, what is my next state when x is 0?
0 1.
Okay. And when x equal to 1?
0 0.
Okay. So similarly for 0 1, what is the next state?
0 1. When x is equal to 0, it is 1 1, and when x is equal to 1, it is 1 0.
It is 1 0. Okay. Next, can you tell me for 1 0 it is?
For 1 0, when x is equal to 0, it is 1 1, and when x is equal to 1, it is 1 0. And
Okay.
for 1 1, when x is equal to 0, it is 0 0, and when x is equal to 1, it is 1 1.
It's equal to 1 it is itself 1 1. Okay. So everybody can note down this state diagram. I'll wait for 2-3 minutes.
So,
And in
shall
the
I wait?
meantime, if there are doubts in the previous state table and this one, you can ask the doubts. Sanjana, you can mute yourself.
Thank you, sir.
So once you are done, just write done in the chat box.
Sir,
Yes,
so the output for present state 0 1 should be 0, right?
the output for present state
0 1.
0 1 should be 0, right? That is if you are considering a XOR.
Yes, sir.
But we have considered OR, na?
Okay. So should we change or?
It's up to you, doesn't matter, na? So,
Okay, sir.
okay, so who was this actually?
Shubham.
Shubham says that I want to do with XOR only. Okay, so he wants with this. So this Z will become a 0. Now this is the present state output for that is what 0 1. So on this also, this 1 will become 0. That's the only difference. So this is like we are solving two problems simultaneously. Is that okay, Shubham?
Yes, sir.
But I would suggest that don't do any mischief in this problem. Just write what is there on your screen. But you can always note down somewhere else, but not here. So I'm just rubbing those red things off. Okay.
Sir, when to use which notation? Means here the output we are writing it in the denominator, but sometimes we write uh, on the arrow.
No. For a Moore circuit, we always write like this. And if it's a Mealy circuit, then we write it on the arrow.
Okay, sir.
See, this is Tanishq, right?
Yes, sir.
If it would have been a Mealy circuit, then we would have got something like this: x equal to 0 and x equal to 1. That means for every x, we would have got a next state as well as an output. That is that is the time when we would have written that way. For a Moore circuit, the output is attached to the present state. And for a Mealy circuit, the output is not attached to any state. It depends on the value of x. Have I cleared your doubt?
Yes, sir. Yes, sir. Understood, sir.
So that is why I am again and again asking whether is this a Moore circuit or a Mealy circuit. If it would have been a Mealy circuit, then what you are saying is right. So in that case, I would have not written that one inside the state, inside those circles. For example, I have written 1 0 and below that I have written 0. So that below 0 I would have not written if it would have been a millisecond. Now you will calculate state equations. You will calculate state equations. So QA plus is equal to what? And QB plus is equal to what? So QA plus will be a function of QA, QB and X, and QB plus would be a function of QA, QB and X. So to calculate QA plus and QB plus, you will go for the previous table and from there you can directly fill the statement. So let's go to the next. So now you tell me QA, QB and QX. What are the outputs? Where does the output be 1? Yash, can you tell me where the outputs are 1 for QA plus?
Yes, sir.
Okay, so those who are getting confused how to fill QA plus, let us
Sir,
go
at
to QA.
position 3, it is 1.
So you can see this is not 3, it is 2, no? This is QA plus, no?
Yes, sir.
Right, so this is 0. This is 0, 1, 2, 3, 4, 5 and 6. So at 2, 3, 4, 5 and 6 and 7, sorry. So at 2, 3, 4, 5 and 7. So at 2, 3, 4, 5 and 7, we are having ones. So what is QA plus? Okay, so who will answer this question now? Srishti, can you answer this question? Srishti Sharma? Srishti, can you unmute and talk? Amit Chaudhary, can you tell us the answer for QA plus? Amit? Amit Chaudhary? Okay, Rohit Sawant, can you unmute and answer? Rohit Sawant? Rohit, are you there? Okay, Shubham and Yash have given the answer. Let's check. So this is one pair, this is another pair, and this is the third pair. So three pairs should do the job. and that is QA bar QB plus QA QB bar plus QAX. Okay, Yash has combined the first two terms and written QAX or QB, that is fine. But even if you don't combine and leave it this way, it is okay. Okay. Next is for QB. Tanishk, can you tell me in which positions we are having ones now for QB plus? Tanishk, Tanishk, can you hear me or no? Karthik, give me a voice check. There is
Yes,
no
sir. You're
response.
audible.
Okay. Vishwas, can you tell me at which positions QB plus is 1?
Yes, sir. Please wait, sir.
Hello, sir. Is it 0247?
0,
247
0, 2, 4, and 7.
7?
Let's check that. That is right. So that will give me one pair, second pair, and one isolated pair. So here we have 2, so here we have a QB bar X bar. Okay, just check it. So this is your state equation. So state diagram drawing is not very difficult. The state equations are also not very difficult. It is one and the same thing. Only the challenge here that we faced was calculating the value of QA plus and Q.
Hello, sir. Hello, sir.
Yes, somebody was saying something. I just lost the connection for some time.
Yes, sir.
Yeah, tell me.
सर इन दैट स्लाइड QB प्लस हाँ सर वो साइड वाले का QA बार एंड X बार आएगा ना
Yes, that is right. This will be X bar. Okay, that is right. Actually, I was correcting that only and the network went. So ठीक है. So let's go ahead. Now I want you all to do this problem on your own. Before I go ahead, I want to know this circuit is a Moore circuit or a Mealy circuit.
Hello, sir. Mealy.
So Hemant is saying Mealy. Anybody else wants to add whether it's a Moore or Moore circuit?
Yes,
Sir,
sir. It
Mealy
is.
circuit.
Okay, it's who agrees that it's a Moore circuit?
No, sir. Mealy.
Mini circuit, sir.
Okay, good. So it is a Mealy circuit in spite of I trying to convince you something wrong. Why? Because simply speaking, this X Z is equal to, so first, like I told you, identify the things. This circuit is based on D flip-flop. So here we will have DA and DB. So fortunately, that QA plus and QB plus cumbersome task is not there. But now they are expecting us to reduce the state diagram with the help of a reduced state table. So we have to do some kind of reduction here. Anyway, we will see. So here we have DA, here we have DB. So here I will have QA and here I'll have QB. So you can see that this is connected to QA. This one is connected to QB and this is connected to X. So it is actually very simple, X plus QA plus QB. So that is the value of my Z. From this Z, like you all rightly said, now Z depends on input. That is the present state input. Hence, it's a Mealy circuit. Hence, it's a Mealy circuit or Mealy circuit. Now, some backtrackings are important here. So you can again see here that here we have QA. This is X. And if you look at this term, this is going to be QB. So here this is AND. So X dot QA and this will be X dot QB. X dot QB. And obviously here this will be the sum of all this. So you can write here, I'm just writing it here. dA is equal to XQA plus XQB. And dB. So this term is QA bar, and here we are having X directly. So dB is QA bar dot X. So we get these three equations. You can see two flip-flops. So we should get the two flip-flop input equations and one output equation. Come on, start solving this. Start solving this. By the way, this was an exam problem for 10 marks. I can't remember the year, but yes, it was there. So please copy the diagram. Once you copy the diagram, just write done in the chat box. Now don't get confused with this in. This is actually reset. You can see that that button is going to the reset terminals of both the flip-flops. and this clock is going to the clock of both the flip-flops. So since we have done so much of counters, I want to tell you one small concept now. This is the right time to tell you that. You can see that we had these states like this, okay? I think Sanjana and Mitali gave the answers. We had these states. We were calling them 0, 0, 0, 1, 1, 0, and 1, 1, whatever you like. But I can call this as off state, off. I can call this as red. Then I can call it as green. And then I can call it as orange. So what application I am talking about? I am talking about a traffic light signal. So let's say initially I am in the off state. So I trigger, I make out input 0 or 1. So it becomes red. It stays in red for some time. And then it gets a trigger 1, let's say, and it goes to green. If it is having a trigger of 0 only, then it will stay at red only. The moment it gets 1, it will go to green. Now if it is in green and if it gets a trigger, you know that if the signal is green, it doesn't become red directly. It becomes orange first. If it gets a trigger of 1, it will go to orange, and from orange, if it gets a trigger, it will go to 1. And this thing keeps on happening: red, green, orange, red, green, orange, red, green, orange. So it keeps on happening, and you can have one thing here that if I am in the off state and if the input is 0, I can stay at 0. If I am in the green state, I can stay at 0. And if I am in the orange state, I will stay at 0. So unless I get a 1, I will not change the state. That is the meaning of this state diagram. Now you can see that actually we saw this is an application of a traffic light signal. That is fine. That's not a problem. So now I want to clearly state what is the difference between a counter and a timer. A counter counts states. A counter can count states. So in this is like a mod 4 counter which can count 4 states. But timer will time the operation between the two states. So when you are in red state and if you get a 1, after how much time this 1 should come, that the timer will tell us. The timer will tell us after how much time this 1 should come. So I hope you are now getting the slight difference between a counter and a timer. They are not the same. we know that the pattern is red, then it becomes green, then it becomes orange, and then it again becomes red. So it is always red, green, orange, red, red, green, orange, red. This is the pattern. But this same pattern, let us say it is at Fire Garden, and this same pattern is there at near some signal near the other station. So probably the traffic near the other station would be higher than at Five Gardens. So, but the pattern has to be same everywhere throughout the city. रेड के बाद में ग्रीन आना चाहिए, ग्रीन के बाद में ही ऑरेंज आना चाहिए. So this pattern should be the same, but the timings can differ. So timings can be controlled by the timer, and the counter will see to it that the pattern is fixed or the pattern is as the designer wants. So this is how it is. Now you may ask me, ऐसा थोड़ी होता है, there is a, if there are 4 roads, then there will be one signal here, one signal here, one signal here, one signal. So there are 4 red signals. Fine. So we have 4 reds, 4 greens, 4 oranges. Or for example, there will be 4 red signals. Each one of them will can have 3 greens. So 3 into 4, we can have 12 green signals. Then we will have 4 orange signals. And if there are 4 roads, pedestrians can cross. So we can have 4 reds for pedestrians and 4 greens for pedestrians. So in all, you can see 4 plus 12 plus 4 plus 4 plus 4. So that is going to be 24 plus 4. So in all, 28 signals, 28 states. So if you want to design a 28 state counter, that is a mod 28 counter, then you have to select those many number of flip-flops which can count 28 states. So I think 5 flip-flops can count 32 states. So 28 would come. So with the help of just 5 flip-flops, you can design a traffic light signal control for a road which is having this pattern. So this is something that I wanted you to know. But here what is given to us is the state diagram is given to us first, and then we have to build the circuit. Now what are we doing? We are looking at the circuit and building the state diagram. So our tomorrow's entire discussion would be on how to build a circuit from the state diagram, that is from the given application, how to build the circuit. Okay, let's go ahead. This is the state table. Come on, copy it quickly. Now, just because this is a D flip-flop, the flip-flops that we are using, that is a D flip-flop, you can see that DA is the same as QA plus and DB is the same as QB plus. Why I have made this X and QA and X and QB? So that I could calculate DA, and DB requires XQA bar. So that is why I have also written QA bar. These are broadly the different set of inputs. Come on, write this. I think I have some questions. Oh, rather they are answers. Okay. Asmita, your answer was right. Omkar, also your answer was right. Yes. Any doubts in the state table, please ask. Now here there is no JK, so we don't have to worry about some other logic. It's very straightforward. Whatever you are writing in DA and DB, the same thing will come in QA plus and QB plus. Okay, so let's go ahead.
Sir, 2 minutes.
Okay, I'll wait. So by looking at Z now, you can say that Z depends on X. And this X tells us that this is a Mealy set. If this X would have not been there, then it would have been a Moore circuit. Now Tanish's question. Tanish, now you have to be careful while drawing the state diagram. Now you will write input as well as output. So this is the output when x equal to 0, x equal to 0, x equal to 0, x equal to 0. And these are the outputs when x equal to 1. So I'm just circling the ones which are for 0. These are the outputs when x equal to 0. And the other outputs are for x equal to 1. And now you can see here that the first two are 0, 0 state, then 0, 1, then 1, 0, and then we have 1, 1. So when x is equal to 0, so the states are 0, 0. And when x equal to 1, that time it is 0. if you directly try to draw the next state table that we generally draw for drawing the state diagram, you directly try to attempt that, then according to me, you will get into some errors. Okay, should I go to the next slide?
Yes, sir.
So this is the reduced state table. You can see when x equal to 1, you can see when x is equal to 1, all the time the outputs are 1 only. And when x equal to 0, it is 0, 1, 1, 1. So that is what you can observe here. When x equal to 0, it is 0, triple 1. When x equal to 1, it is 1, 1, 1, 1. And when x equal to 0, this is the next states are whatever by looking at the present states. Okay, so now time for some question answers. So please build this state tape diagram. Okay, Ruchira Gupte, can you unmute yourself?
Yes, sir. Yes, sir.
Ruchira, how many states can you see?
4, sir.
4 states. Okay. So the 4 states are 0, 0, 0, 1, 1, 0, and 1, 1, right?
Yes, sir.
Now, listen to the question. If my present state is 1, 0, if my present state is 1, 0, what is the output and the next state when x is equal to 1?
Next
my
state
present
is 1,
next state is
1, 0 and output is 1.
next state is 1, 0 and output is 1. Okay. If my present state is 0, 0, and what is my next state and output if x is equal to 0?
Next state is 0, 0 and output is 0.
Next state is 0, 0 and output is 0. That is right. So this is what you mean by that.
Yes, sir.
Okay. And if x is equal to 1, what is the next state?
0, 1.
And the output is
1.
1. So now can you all complete this state table? So if I am in 0, 0, if x is 0, then my next state is 0. and output is 0. So that is what I write here. The next state is 0 only. So this is my X and this is output Z. So similarly, if Ruchira, can you complete this 0, 1?
Yes. When present state is 0, 1, then at x is equal to 0, next state will be 0, 0, and output will be 1.
Okay. Next.
And when x is equal to 1, next state will be 1, 1, and output will be 1.
Okay.
Then
For
at
0.
present state 1, 0, when x is equal to 0, next state will be 0, 0, and output will be 1.
Okay.
And when x is equal to 1, next state will be 1, 0, and output will be 1.
Okay.
When present state is 1, 1, at x is equal to 0, next state will be 0, 0, and output
Okay.
will be 1.
Okay.
And at x is equal to 1, next state will be 1, 0, and output will be 1.
Okay. So this is your state diagram. Good. You can mute yourself. So this state diagram is not very difficult. This just reminds me when we were in engineering, we used to get 8 states and 2 inputs and so many outputs. With that, this entire thing becomes really very tricky. Okay. So let's go to the next slide. Now, what they are telling us is that if this is your table, reduce this. So we have to reduce this table. So what are the rules for reduction? First, I'll replace all these binary terms 0, 0, 0, 1, 1, 0, and 1, 1 with A, B, C, and D. So let us derive the state equations. The state equations are simple. So QAX, QBX, and QA plus. So just note down the second K-man. And this is just QA bar X. So the first one is for QA plus, the second one is for QB plus. But you will write only the second K, directly this. And after doing this, now you will go to state reduction. So those who have completed the K-maps also go to state reduction. Okay, so let's move to the next slide. Now you can see that the top table is similar. So this table is similar than what we have drawn before. So don't draw this table. The upper table you don't draw. Only the lower table you will draw. So what I have done here is this is A, this is B, this is C and D. So accordingly you will replace here also everything with in the same way. So this will be A, and this will be zero one is B, 1 is T, 10 is C, this is also C. So you can see that in the lower table I have just replaced 0001, 10 and 11 by some characters A, B, C and D. Now you can see directly that state C and D are similar. You can observe that state C and D are similar. So don't draw this, draw only the second state table. First is only for reference. If I say 00 is A, 01 is B, 10 is C and 11 is D, then accordingly in the next state outputs of flip-flop, those two columns, we have to write A, B, C, like that. So please note the state table. Okay. Parth Thakur, can you unmute?
Yes, sir.
Parth, can you tell me which two states are now similar? Is state A equal to state B? Is state A equal to state B?
No, sir.
Why?
Because A is 00 and B is 01.
No, that is not the answer. That your answer is right, but your justification is not correct. So you can see here, I am asking you whether state A and B are equal or not. So they are not equal because their outputs are not the same. Their outputs are not the same. It is 0, 1 and 1, 1, right?
Yes, sorry, sir.
Okay. Now can you tell me whether state A is equal to C?
No, sir.
Why?
Output for A is 0, 1 and that of C is 1 and 1.
Okay. Now can you tell me whether states C and D are equal?
Yes, sir. C and D are
States
equal.
C and D are equal. Why they are equal?
Both have the outputs 1 and 1.
And what is also equal?
B and D.
No.
Sorry, sir, I didn't get your question. Can you
Is
repeat again?
state C and D equal? Are they one and the same? This state C,
Yes,
this
sir.
is state C
Yes,
and D. Are they equal or not?
they are equal, sir.
So now why they are equal, you tell me. You said outputs are equal, fine. We can see that the outputs are equal. And why are they equal? And only outputs being equal is not the necessary condition. There is one more condition. What is that condition? Okay, Altamash Khan, can you unmute? Altamash? Shruti? Shruti Biani?
Sir, Tanish speaking.
Yes, Tanish?
Sir, actually, I had some electricity issue at my home, so can I answer all the next questions?
Yeah, you can, but let us give some chance to others also. If they don't, then definitely you can.
Okay, sir.
Yes, sure. Shruti Biani? Is Shruti there? Okay, Tanish, can you come in and tell me why states C and D are equal?
Yes, sir. As you said in the previous lecture, for two to be equal, there are two necessary and sufficient conditions. The first condition is their output should be equal, and the second condition is their next state output should be equal. So in C
Yes.
and D, satisfies both the conditions. So therefore, C and D are equal.
Okay. Parth, can you just unmute? Parth, now you can see the outputs are equal as well as the next states are also equal. You can see here the next state for C when x equal to 0 and x equal to 1 is A and C, as well as for D also it is A and C. So this next state and output for two states to be equal, both of them should be the same. Then only we can say the states are equal. So we can see now states C and D are equal. So that is the reason why we can eliminate one state. So out of C and D, we should eliminate the state with the highest state assignment. So the highest state assignment is 1 1. So 1 1 is for D, and that is why we eliminated the D state. और simply speaking, जो सबसे नीचे है उसको निकालो. The one which is the lowest in the table, remove it. So we can remove state D can be eliminated. So once we eliminate every D can be replaced by C. Every D can be replaced by C. So now you can see here that here we had a D, but now we are eliminating D. So that is why D is equal to what? C. So every D is now replaced by C. So this is what we get. Now can you tell me, just a minute, Asmita, Asmita, can you
Yes, sir.
unmute? Yeah. Now can you tell me out of A, B and C, which states are equal?
B and C are equal.
B and C are equal. Why they are equal?
So because the output as well as the next state of the flip-flops are similar.
So these are the outputs. Are they similar? 1, 1, yes. And the next states are A and C. So even they are equal. So that is why they are similar. So now we can say that state B is equal to state C. So I have just highlighted that. Okay, Asmita, you can go on mute. Now, Asmita, just hold on. Out of B and C, which state should I eliminate, B or C?
C, sir.
C. Why C?
So because we should always go for the highest bit.
Highest?
Highest bits.
I will just add one word to it, highest bit value. So that
Yes,
is,
sir.
if this
Sorry,
is
sir.
0, 0, 0, 1, and this is 1, 0. So out of B and C, who is having the highest bit value, which is 0, 1 and 2. So we'll eliminate this C. So we'll eliminate the C state. That is right. State C can be eliminated. And now every C can be replaced by B. Every C can be replaced by B. So I wrote C equal to B, and then I just replaced it. Now Asmita, again, are you there?
Yes, sir. Yes, sir.
Now is further reduction possible? Is state A equal to B?
No, sir.
Why?
So even if the next state of the flip-flops are looking similar, but the outputs are not equal.
Okay, that is the right answer. So everybody listen to what she's saying, that the next states are same. For x equal to 0 and x equal to 1, the next states are A and B respectively for both states A and B. But this AND condition is getting violated. That is, these conditions, that is, the outputs are not same. So the outputs are not same. And hence, state A not equal to B. And that is why further reduction not possible. Further reduction is not possible. And hence, my reduced state table becomes this way now. Simple. I had four states before. Now I have only two states. That is A and B, which I write it as 0 and 1. And basically I have only two states. And from that, I make my state diagram. So just I'll quickly go to the state diagram. So this is the reduced table, which is there at the top. You can just copy that. And my state diagram will have only two states, 0 and 1. If x equal to 0, the next state is 0 and the output is also 0. If it is 1, the output is 1 and the next state is also 1. If my present state is 1 and if x is equal to 0, then the next state is 0 with output 1, and if x is equal to 1, the next state is 1 itself with output 1. So we could reduce the state diagram. We are reducing the state diagram means the same circuit which had got two flip-flops. Now we can implement this flip-flop, this circuit with just one flip-flop. So other things are pretty much redundant. Okay, so it's 4 o'clock and it's time to end the class. Just a minute, I am taking the attendance. I will just continue, just wait. Okay, so you all are free to log out. And I am just keeping